Right, well, I think the recording started. Hello. Oh, I should do the tradition. Which way is this pointing? Oh, it's right there. Hello, I'm David, and I'm the coordinator of the Maths Learning Centre. It's semester 2, 2019. Freaking me out to be nearly at 2020. This is a revision seminar for Statistical Modelling Inference II, a course which I'm sure I did some version of at some point in the past, but it's been a while since then, and some people trust me a lot to let me do a revision seminar for this. So I'm going to be making up a lot of stuff as I go and trying to make sense of it from the resources that the four students who are here have. Those of you watching online, I hope it's helpful. Yeah. Okay, so the thing I've been specifically asked to talk about is ANOVA/ANCOVA, and I'll get there, but first I'm just going to talk about my sort of general idea of what regression is doing, because this course, as far as I can tell, is about regression. Like in regression models, and there's X's and Y's and betas. Yep. That's my general idea about what this course is about. So I may need to rely on some people for lecture notes / slides. If you have files, feel free to send them to me. If you can find which lecture it's in, I can have a look, or I can look at your handwritten notes if you don't mind them appearing on the video. So, yeah. So, first I just want to talk about my general idea of what the majority of statistics is about, which is predicting things, basically. So the idea of statistics is you have some sort of outcome, and you'll have some sort of things predicting it. Your lecturer in the School of Maths is likely to call them explanatory variables. I'm not sure. Or predictors. And so there will be various things that you think make a difference to this outcome. That's how I think about regression. And they're all like this. And what we would like to do is create some sort of formula that predicts this from these things. That's the idea. A formula involving x1, x2 and x3 plus some randomness. So in other courses I've played a game, which I could play with you, but I might just describe how the game works in this one, where the game's called Guess My Rule. Sorry? We played it in SAM, right? It's called Guess My Rule, and I say, you give me a number. Well, the classic one I love is you give me a letter of capital or small letter of the English alphabet, and I give you a number, and you have to guess the rule by which I'm deciding the number. And so you can use the information you have about those letters to try and guess what rule it is, and it turns out that the rule was something like the number of holes that it has plus 1 if it's a vowel, plus 2. And that's cool. But there's another game I play where I say, guess my rule, and you say, you give me a number and I'll give you a number, and you give me a number like 10, and I say, okay, 101, and you give me a number like 5, and I say, 52, and you give me a number like 8, and I say 86, and I do all of these things, and people get extremely frustrated because then they say 8 again, and this time I say 84, and the point is that in statistics, it's not like there's an actual function that actually predicts the outcome. It's just like, well, you can get close, and then there's this other bit that's random. And that's the idea. So that rule was times 10 plus what you get when you roll a die. And so that's the idea of statistics. And our way of trying to get a handle on this is to try and get as close as possible to the bit that isn't random. And everything left over, we just hope that it has the right sort of random for us. And we just assume that that bit's normal. And that's the general idea of regression. Okay, so the formulas tend to look something like, you know, something like that. Does your lecturer use epsilon? Okay. Cool. But then here's the thing, specifically, this is a statement about random variables. And each specific y that you get will be a specific value of this random variable. And so most of the time you'll see it something like this. Which order does your lecturer put the i's in? I1 or 1i?
Depends on the context.
Whatever. I will just do this.
Yeah.
So this is the random variable one.
Yeah, the I1.
Yeah, I want.
It's all good. It's fine. And this one is the specific value ones. Though technically I think it's still random variables. People are a bit sloppy about their capital letters and small letters and stuff. These become little x's. Okay, and then I'm pretty sure in the theory that these capital X's are in fact never random variables. We just assume that they're not random. They're fixed. Because usually in the situations where you use regression, it's like a scientific experiment and you actually do get to choose what the x's are. And so you choose them and we see what happens when the y comes out. And that matches better with our guess my rule thing, where you get to choose what the input is and then we see what the output comes out to. Okay, cool, doing okay. But this picture is what's in my head almost all the time. Okay, that there is a variable that we're trying to get a handle on how it changes, and we have these other things that we think are going to predict it. And that's what's in my head. And all statistics, I would tend to draw a picture like that first in a specific story. Okay, and there is no particular reason why those variables can't be categorical, except that categorical variables won't work in a mathematical formula, so I'm going to have to turn them into numbers somehow. And the classic way of doing that is to say 0 for no and 1 for yes. Cool. We're doing okay? Right. So that's my general understanding of how this works. And then just a minute. I'm just looking at my screen to see. Well, they haven't told me how to draw them. No. Okay. Right. So this formula is traditionally linear, but it doesn't have to be. You can multiply the variables by each other and have all sorts of crazy stuff, but the linear ones are easier to cope with. Okay. Well, at the very end you have ones with x1 times x2. But that's usually only when they're factors, like categorical variables, and so it technically counts as a whole variable of its own. Okay. So the idea is that when we take this, let me step back. The other idea, which comes from Fisher in the 1920s, is that your data, if you've got like 20 observations of y, that is a vector with 20 coordinates. And so statistics is really linear algebra, which is fabulous. And Fisher was extremely smug about this and refused to explain it to anyone who didn't understand already. Sometimes I say the tradition in statistics teaching has continued to this day, but maybe not. Some people are a lot better than that. But yes, he wasn't a very nice teacher, was Fisher. He was a very smart person and had friends, but wasn't a good teacher. He was a nice person to his friends, but not a good teacher. We can turn everything that we have to say about this, about the individual ones, into a big matrix thing, a big vector and matrix thing. And so just checking that I've got the same understanding as everybody. So you might have something like, you've got a measurement. Let's pretend they're people, and you've recorded y1 and x1 and x11 and x12 and x13. That's how your lecturer normally does it, with the person first. Right, the individual first, and then this person will have, y2 and x21 and x2. I think it's that way so that it works well in the matrix when you do it later, and so on. Okay, and so on. And then what you can do is you can make a vector of everybody's y's, right? Like that. And traditionally that's called what? A bold y, probably? Or just y? I don't know. I'm just going to look in the lecture notes.
When you write something with slides, it's bold by hand, it's just a bold by. Should be a vector. Very slides, actually, y bars and y bold bars.
Yep, it's a bold capital Y, apparently. Great. Okay, capital Y in bold, because it's a vector. Anyway. Okay. And then what you can do is you can turn all the values of x into one big thing. But it's going to take me a while to get there because I need to do it via the equations. So we know that y1 is beta naught plus beta 1 x y1 1 plus b2 x2 1 b3 x3 1 plus epsilon 1 and so on, right? Every time I learn this I have to do all of this from scratch. Oh crap, that's x12. See, no, that's right. Right, something like that. It freaks me out because I think that it should be like it's the variable x1 and it's the second one of those, and so I feel like it.
2, 3.
Sorry?
On your last one,
Well, just.
Yeah, you've got beta 1, 3x.
I think we'll get
It doesn't matter. Like in my head, it should be variable 1, the first one, variable 1, variable 2, the first one, variable 3, the first one.
We do ours the other way.
Yeah, and you do it the other way. You do it person 1's first observation, first x, and person 1's second x, and person 1's third x, right? Yeah. So this one should be that, and this one should be 1, 2, 2, 2, and 3, 2. Yeah? Because it's person...
That should be 2, 3.
Right, and this should be 2, 1. And this should be 1, 2. And this should be 1, 3. See, I always get that wrong. It probably doesn't make any particular matter once you get to the, as long as you put things in the correct positions in the matrices. And so on. And so this vector is equal to this vector. And so what I would like to do is write this as matrix times vector. And the matrix is going to contain all the x's, and the vector is going to contain all the betas. And actually the error bit's just going to be tacked on the end. So there's 3 pieces here. So the order I do it is, you know, epsilon 1, epsilon 2, and so on. And then the betas are all going to be here, like that. And then I have to describe how I multiply what's in this row by this column to get that answer. So I have 1 beta naught and x11 beta 1s and x12 beta 2s and x13 beta 3s, and magically now the 1s are in the correct position to say it's in row 1. Yay. So we have 1 beta naught and x2 1 beta 1s and x22 beta 2s and x23 beta 3s, and so on. And I'm pretty sure your lecturer will call this y and this capital X and this beta, like the vector beta, and this the vector epsilon. Yeah? Okay. Good. Okay. So, and that's just a magic trick with the algebra, and it allows us to write everything we could try and think of in that way, as long as it's linear. Because if it's not linear, then it's going to be a lot harder, because you won't be able to do it with matrices if it's not a linear function of the betas. So it is okay to have things like x1 times x2. It's just that that will have a coefficient of its own, and what's in this entry will be x1 times x2 in that position. Cool. That's the big idea, and that means, and the reason the matrices are so useful is that it's actually technically how the computer's programmed in the background. Like there's a matrix, and there's some cool little things with transposers and inverses and stuff where you can say, well, and therefore the correct answer for beta is something like an x transpose x inverse times x transpose y. Yeah. Something like that. Cool. And that comes from orthogonal projection. Yeah.
Maybe you have to know the proof of the
You have to know
whole.
the derivation.
Sorry?
You have to prove that it's the base square test.
Okay.
You don't have to do it.
Oh, that's not that. Wait.
You did the clause in 2 ways.
It's just some,
Or you can.
at least the multi-linear case.
You can do the
Okay.
alpha,
So let me just check something. There's this idea that we know that because we don't really know what's going on with the random bit, that we might say that given a specific set of x's that we think of, that there would be a y that goes with it. And you know that there's randomness involved, so it won't be exactly that y every time, but you're thinking that's going to be like the average y that we're expecting. And so what we want to do is we want to choose our x's, we want to choose our beta hats, because we don't actually know what beta is, that's the problem. Our problem is that we imagine that y is x times beta plus epsilon, but we know neither what the beta is nor what the epsilon is, we only know what the x's and the y's are. So this is the idea. We know this from our data, and we know this from our data, but these are both unknown. And we don't know what they are. And there are many choices of vectors beta and epsilon that would make y equals x times beta plus epsilon. There are many of them. To be fair, you could choose any beta you wanted and you just figure out what the epsilon is by going y minus x beta. And so there are infinitely many choices for what beta and epsilon could possibly be. And we want to choose them in such a way that the y is somehow close, this epsilon is somehow as small as it can possibly be. That's what we want to choose. So we want to choose And what the hell does it mean for a vector epsilon to be small? So it could mean that you want all of the values of epsilon to be as close to 0 as possible. That's what it means. Yep, but you could also say, well, just a second, I could say that the vector as a whole, as a point, should be as close to the origin as possible. I want this vector to be as short as possible. So I'm going to do this. It's a vector, I can make that vector as short as possible. The length of that vector, crossed out the small and put in short instead. I want that to be as short as possible. So what I want is the length of this vector. And the length of that vector is the square root of the square of all of the individuals, and so we square all the epsilons that we calculate from all the different betas, and we try and choose the betas so that that answer is as small as it can possibly be. And that's called the sum of squared differences, I believe. Normally SS in ANOVA Q. And so you say that Q is like this is the length of that squared, which is the sum of each entry squared.
Yeah.
You know, yi minus beta naught minus beta 1, blah, 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 squared. Okay, because we don't really need the square root. If the square root is small, then the square will be small and vice versa, so that's all good. And this will be different for different choices of beta, and what we do is we try and choose the beta that makes it as small as we can. Right, but are you ready for the linear algebra magic? As far as I'm aware, I mean, you can do it with calculus if you want. You can differentiate it with respect to all of the betas and make all of those derivatives 0, and that should tell you where the minimum is. That's one way. And the other way is to use linear algebra and say, well, yes, but we can also do it subspace-wise. So one way is to say, so I'm just going to say them both, you know. So one way, you know, QB is like a function of beta naught up to beta however many there are. And so what we can do is we can go dq on d beta naught equals, and set that to be 0, and dq on d beta 1 and set that equal to 0, etc. and solve those equations simultaneously, and it will tell me what the betas have to be to get it as smallest as possible. In terms of x and y. That's great. So that's one way. I don't know a way of doing that matrix-wise, because that's some weird-ass crap. But the other way is to realise that the set of x betas such that beta is in R whatever it is, Rk, is a subspace of R whatever it is. Because if you've got a matrix, yep.
There's beta naught. So you've got like a beta naught plus x1 b1 plus. Isn't that beta naught shifted so that it's like not a subspace? It's like that.
It's not important. Because the beta naught is part of this vector, and this matrix just has ones. So you're thinking a good way, but it's a different way. Okay? So because we get to choose what beta naught is, that just means that 1 is one of the entries of the vector that we're using as a basis.
Just got another dimension.
Yeah. So if you've got like that, if you've got that, right, this is a linear combination of the numbers 1, xi1 up to xik. So what we're saying is that when we do y, which is beta naught times a whole lot of 1s, plus beta 1 times plus dot 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 beta k like that. I mean, that's what we're doing when we make the matrix. Like, this is the same as this, right? You know, plus epsilon, right? So when we make this matrix, we can think of it like this, and this is a span of vectors, which means that without the epsilon, it's a subspace. That's what we're doing. Span. So when you multiply a matrix by a vector, and you multiply it by all the possible vectors, what you get is a subspace. So this is a subspace of Rn, and what we would like to do is we would like to choose the point in that subspace that is as close as possible to y. That's what we want to do. So we want x beta to be as close as possible to y, because that's what we want. We want the epsilon to be as small as we can. And so therefore, if you have a subspace and you have a point outside it and you want to find the nearest point in the subspace to that, that's the orthogonal projection of y onto that subspace. I don't know if there's a name for this. I shall call it W because that's what we called it back in Maths 1. So, i.e. the orthogonal projection of y onto the subspace W. That's what we want. i.e. x beta is the orthogonal projection of y onto W. And so you choose beta so that x beta is the orthogonal projection of y onto W. And there is some magic linear algebra that you can do that shows that it is what it is, with the transposes and the inverses and stuff. So, yeah. Yay. Okay. So are you supposed to be able to derive this?
We have to do a proof of it.
Prove that it's the least. You don't have to derive it, we just have to prove that it's the least.
You have to prove that it's the least. Okay, so my understanding of that proof is that you have the answer already, and you show that every other answer is further away. Okay, do you want to do that? No? Okay, cool, that's all right. So it turns out and you call it beta hat, right? Good. Okay, so is it this? Yep. Because then if you put like x beta hat in for y, you get beta hat. Yeah, cool. Like just if y is x beta plus epsilon, right? And beta hat is.
So the inverse is outside the brackets.
Oh yeah, thank you. Because x isn't necessarily square, so it doesn't have an inverse. And that is beta, because this cancels with that. So what you want to show is that, yeah, cool. Just thinking it through, I'm justifying it to myself by going, yeah, it's about right. Beta hat is approximately beta if I sub in the actual answer. Yeah.
Doesn't that show the expected value of beta hat this way?
Yes, it does.
Expected value of
Because the expected value of epsilon is the vector of all zeros, right?
somehow one is constant.
Yeah. Are you allowed to use expected value for matrices rules, where you can just take out a matrix out of the expected value?
I think one proof we did, and there was one tutorial question on it, but we didn't actually go through it.
It should work because expected values are linear and matrices are linear. Like matrix multiplication is linear. Cool. So this proves that the expected value of beta hat is indeed beta. That's cool. Nice. So just some. Right.
Expected value of epsilon is 0.
Yeah. So the expected value of each entry of epsilon is 0. So therefore the expected value of the vector as a whole is 0. The 0 vector. Yeah. Okay. And so really actually you should be figuring out what eta hat is. Because like, yeah, because we don't really know what eta is either. Yeah. So I guess if you wanted to prove it, you would say, well, that's what beta hat is.
Did you say eta?
Oh, sorry, eta. No, wrong letter. Epsilon.
Because eta's what we use.
Eta's the capital H.
Yeah, we use that for B.
It's like a statistic that you calculate.
Using those as the expected. I think the expected value. No, we
Yeah,
use
no,
beta exacts beta. Beta. Yeah.
Yeah, we had like that. Eta was it doesn't matter.
Oh, this is called eta, is it?
Yeah, I think, or is that what
that
we
is,
use?
yeah,
Or-
so the expected value of the vector y was vector eta.
Yeah.
That makes sense.
It's the notation we use.
Fabulous. We used up the whole Greek alphabet yet.
Yeah.
Okay, so I think that if epsilon is, if you sort of sub this back into the formula to figure out what epsilon hat is, you can make epsilon hat as short as possible by picking this, because if you picked anything else it would be bigger. Right. Okay. I don't want to do that proof today because that's not going where we want to go, but I just wanted to make sure I understood all the details of what's happening so far. Okay, so in ANOVA, I'm just going to write this as the preliminary ideas, and now we're actually up to ANOVA. So the idea of ANOVA is this. You have y, which is a number. I'm just going to write this because it's a number. It's got a scale on which to measure it. And you would like to predict what y is based on a category. That's how I think about ANOVA.
Is it always category, or is it the sum of a?
Well, traditional one-way ANOVA. So in my head, this is what the the research question is like. So I would say something like, you know, I have 3 different varieties of wheat, and I would like to know the yield per hectare in tonnes that I get from those 3, and I'd like to see if they were all the same or not. And that is actually what Fisher used it for. when he invented it. So, okay, it's pretty boring, but, you know, it paid the bills. That's the idea. But, you know, the classic thing in medicine is where you have like 3 different treatments. You've got the placebo, and then you've got then 2 different treatments. You give everyone those things, and you measure, say, their blood pressure, and then you systolic or diastolic, doesn't matter which one. You measure one of them, or their glucose levels after their diabetes glucose test, or whatever. You measure a number on them, and then you compare those numbers across the 3. And so your graph, if I was drawing a graph, would look something like this. And, you know, X comes in 3 categories, like A, B, and C, and then Group A might be like this, and Group B might be like this, and Group C might be like this, something like that. And that's what the graph would look like. And we'd be wondering, well, is it possible to predict what Y is based on which category you're in? But the real question you usually ask is, are the means of the Y's that come from those 3 categories the same or not? Yep.
So in this brief for A and C,
Hmm?
like, are you assuming that A is 1, B is 2, C is 3? Or
Nope,
something like that?
they're just categories.
Just categories. Okay.
They're literal words. Now, this is not going to work in our traditional way of writing these things, because you can't put the letter A in your formula and get an answer out. I mean, you can, but not in any reasonable way. So what you need to do is turn this into a different question entirely in order for the system that we're doing with the matrices to work. So what we're going to do is we're going to choose one of these to be like the base category. And if you were doing medicine, you would choose the placebo. You know, people get the pill, but it's actually just got sugar in it or something. And if you were doing most things, you would choose whichever category of that to either probably be the most common category, or the one that doesn't do anything, that you're pretty sure isn't going to do anything. That's what you do. So you have to choose one of them to be the base. Usually placebo or most common, or least common. All right, pick one. Yeah, sorry, or least common. It doesn't really matter, and that writing was really bad, partly because I'm writing too fast and partly because my pencils needs a sharpen. So there was an example in the notes that had pets, and they were dogs and cats and rabbits, and your lecturer chose rabbits as the base category. Because nobody cares about rabbits, and you really only care about dogs and cats. I mean, if you go to any vet, actually they normally only care about dogs, and cats are like, they're fine, and I'll treat them, but I really care about dogs. Or to the show, right? There's always stuff for dogs. It's never stuff for cats. And that's partly just to do because they're working animals on a farm, and cats are not. Cats spend 18 hours a day sleeping. Sorry? Yeah. like scratching you for no reason. And I mean, I love our cats. Our cats are beautiful, but that's what they do.
They make me sick. So.
For most people, if you're not allergic to them, they lower your blood pressure.
Really? So everybody's still a little bit allergic to them. Sort of like how we're all just a little bit allergic to them.
No, it's more that if patting a cat lowers your blood pressure, it makes you feel better.
Oh, okay.
Unless you're allergic to one, then it just makes everything worse. So, okay. And maybe that's our new study, right? We have whether you're allergic to cats or not. There's probably 4 categories, like whether you're allergic to cats and whether you like cats, and then your blood pressure after patting one. Compared to before. Okay, so you choose a category to base, and what you do is you have each other category has a variable of its own to say whether you're in that category or not. So whether you're in that category. So 0 for no and 1 for yes. Okay? And so if you get all no's, then you know you're in the base category. So in this example here, you would have like a variable xc, which is 0 if in category C and 1 if in category if not. And you'd have xb, 0 if in B and 1 if not. And there is no variable for category A because you don't need it, because if the other two are 0, you know you must be in category A. So there's no XA, since if XB is 0 and XC is 0, must be in category A. That's the idea. So you need to choose whichever category you think that makes the most sense for. So in medicine, the placebo. Really, generally, you choose the base case to be the one you care the least about. Really? Okay. And so what that means is you can now turn it into this. Which has two categories now. How do these two new categorical variables we've created relate to the value of y? And you would say something along the lines of something like that. This is where I might be leaving what your departing from what your lecturer does when they do they describe ANOVA. Just give me a second. No, that's right. Okay. Why is this so complicated? It really shouldn't be that complicated. Okay. Your lecturer has used mu's and alphas. Okay, but this is the idea, like all things that are of this flavour of that type. What you need to figure out is how these things are related to the question you might want to ask. Now, I never ask a question about means, I don't care, I only ask about relationships. But people who write statistics exams care about means, and people who do research care about means, and so that we need to go with that, make them all feel better. And so we can think about what the average would be if you were in various categories. So if you're in category A, then that means that XB is 0 and XC is also 0, and so we actually get that Y is beta naught plus epsilon. Like that. And so what that means is that in that situation, the mean of the Y's will be beta naught. Because the what's this thing called? The expected value of the epsilon is 0, and so therefore the expected value of the Y will be the beta naught. And if we're in category B, then XB is 1 and XC is 0, and so we get that Y is beta naught plus beta 1 plus epsilon, and so therefore the mu in category B is actually beta naught plus beta 1. And so to ask myself, is mu A different to mu B, is to ask, is beta 1 0? And I'll just do it for category C as well. If in category C, xb is 0 and xc is 1, and so y is that, because this one's 0 and that one's 1, and so therefore the mean in category C is beta 0 plus beta 2. So to ask is mu 1 equal to mu 2, mu A equal to mu B, that question is to ask, is beta 1 equal to 0? Because beta 1 is the difference between mu A and mu B. And to ask, is mu A equal to mu C, is to ask, is beta 2 equal to 0? Because beta 2 is how far mu A and mu C are. And to ask, is mu B different to mu C, is to ask, is beta 1 different to beta 2? And so, is mu B equal to mu C, is to ask, is B1 equal to beta 2? So you notice that none of those questions are about beta 0. Beta 0 doesn't really matter for these questions. And so finally, to ask, are they all the same, is to ask, are beta 1 0 and beta 2 0 at the same time? Because if they're the same, if mu A and mu B and mu C are all the same, then beta 1 and beta 2 would have to be 0. Because that's basically asking, are they all equal? It's the same as asking, are they all equal to mu A? Because they're all equal to each other. Now your lecturer's done things with betas and mu's and alphas. That's what they're getting at. I find it much easier to just do this and then think about what the means are in terms of these. So basically the magic trick is that if you set up your one category variable with multiple categories and turn it into several categorical variables, one for each category except the base category, then asking are the means all the same in these different groups is the same as asking are all my betas other than beta 0, 0. And what that means is you can compare how much variability, like how far away your predicted answer is from the real answer in the situation where the betas are all 0, and how far away the predicted answer is from the real answer in the situation when they're not, and see which one has the most variation. You go, well, you know, this one's pretty good. That's my understanding of how the deal goes. All right, now let's talk about this ANOVA table. So now what we've managed to do is we've managed to turn the question of are the means all equal into a question about these betas in my regression. Okay. Okay. I'm just going to... I can't be bothered plugging this in because I have to go all the way back to my office to do that. My computer screen. That's an ANOVA table from your lecturer's lecture notes. I don't want to put too many of the slides because technically that's a copyright issue. Though technically all things made by any lecturer at the university for the purposes of teaching belong to the university, not to the lecturer. So I should be allowed to use it for educational purposes. Okay. And this is an ANOVA table, which is apparently a way of us figuring out what's going on here. And suddenly, things are confusing because now we have yij's instead of just yi's. We're going to have to go back and relabel all our variables. Crap. Okay, that's all good. I'm fine. Sorry?
Why don't you just write the table notation instead?
Well, we need that. We need it to make sense of something here. Okay. Okay. No, just give me a. Because do we have this? Do we have this in matrix version at all?
No, we do the matrix stuff, I think. When we do it later, when we do the formulator as linear regression.
Okay.
Like, we originally looked at it not as linear regression.
How far away from this lecture is that?
Reasonably far.
Can you find it?
Which lecture I get 24?
Okay.
Can you find the
I can tell you how I understand ANOVA to work. We can do it with the linear algebra as well. I mean, we can totally do it with linear algebra. We can do it with both. But this is my understanding of how ANOVA works, and it goes back to this picture, and I'll do it with my 3 categories. Okay. So these are the 3 categories for my variable, which I will turn later into 2 different variables, but that's neither here nor there. We know that the mean of A, or I might make A smaller if that's okay for the purposes of the picture, because it's going to be easier to think about. So we know that the mean of A is beta naught, based on what I said before. And we know that the mean of B is beta naught plus beta 1, and this is beta naught plus beta 2. So that's mu A, mu B. And we're assuming everything's normal, so it should, the mean is in the middle. And the mean of anything's always in the middle, so it doesn't really matter. Unless it's horrifyingly skewed and has like infinite variance or something. So that's what it's looking like at the moment. This really should say B. It looks like a C from this distance. There we go. Okay. All right. So, cool. So what we're going to try and do is we're going to try and compare how much variation there is if I consider this is all just one big group, and how much variation there is if I consider that it's not. So if the beta 1 and the beta 2 really are 0, my question is, how likely is it for this to be so far away from the mean I was expecting? The mean of group A. Right. Okay. So if the beta 1 and the beta 2 really are 0, the best estimate for beta naught is actually the mean of everything, because it's really just one big group. So if like that, put them all together. It's one big group, doesn't matter what A, B or C is, it's one big group. And there'd be some grand mean here. Okay? So what we're doing is we're comparing this story when we think the 3 means should be considered separately to this story when there's really just one big mean. That's what we're doing. And so what we can do is we can look at how much variation there is around the mean here compared to how much variation there is around the local means here. That's what we're doing. So I don't know if the lecturer explained it this way. Do you know? Roughly? Okay, but we're not really doing it individually there, we're really doing it in multi-dimensional space, right? And all the distances are actually lengths of vectors. So we're going to be squaring things and adding them up, because that's what's really going on in the background. But it's okay for us who don't live in n-dimensional space that we're aware of most of the time to think about it as distances. And so what we can do is we can look at every individual in our data. So for example, this individual here, who is in this picture here, right? And I can say, well, how far are they from their local group mean? And I can think, how far are they from their grand mean? And those two distances will be made of how far they are from their local mean, plus how far the local mean is from the grand mean, should be how far they are from the grand mean. Yeah. So I'm just going to draw that in a single number line. So here is YB, like 7 or something. I don't know which one it is, but that's what it is. And like here is mu B. And here is the grand mu. And I know the distance between this and the grand mean is combined the distance between this and the local mean and the distance between the local mean and the grand mean. And they go together the way they do. It's much easier if everything's positive and everything's way above both of them. But those three things go together. Okay, that's the idea. And so those three numbers are going to be interesting to me. And what I'm going to do is I'm going to square all three numbers, because it's all about vectors really. And because I'm really thinking about how far the subspaces are from each other. I'm going to square all three of those, and I'm going to add up the square distance of everything from the grand mean, and the square different distance of everything from the local mean, and the square distance of all the local means from the grand mean. But that number has to be taken into account for every one of the data points. And those three numbers I'm going to compare to each other. I don't really care about the distance from the grand mean. I just care about the distance of the local mean from the grand mean. Because that's how much variation there is. Right. Okay. I think the idea is that if the group means are different, the best estimate for any individual in any group is their group mean. And so you're really interested in how far the group means are from the grand mean. Okay. My understanding is pretty shaky on the details, but that picture helps me remember what to do. So, basically, the sum of distance to mu squared should be the sum of distance to local mean squared plus the sum of distance from local mu to big mu squared. That's the idea I'm thinking of. So the distance to mu squared is the distance to a subspace where everything has the same value, because our best estimate, if they're all the same, is just the same number for everybody. And that's a subspace. It's the subspace where x equals y equals z equals whatever. And the distance to the local mu is the one that has three different means for those things. Okay, so it's all about subspaces. Right, cool. And so that's what these things are. So that means we're going to have, that means we need notation for the y's that tells me which group they're in. And that's why there's i's and j's in this thing here. And the dots and stuff. And so this is saying, when we have that notation, there's now new notation y I, j, give me a second. Yeah, thank you. Yij. If I read this, they're within groups. This one here is supposed to be the distance between each individual and their local mean, the one that belongs in their group. And so when it says I dot, that means you do the mean adding up, keeping this one the same. No, we add up across that one. And we keep all the i's the same. Yep. Okay, so the i's, so the j is which group, no, the j is which element you're in, the I is which group you're in. And see, now it's backwards, damn it. So this is which group you're in, or category if you like, and this is position in the group. So, you know, group A, fifth individual piece of data in that group. That's the idea. Okay. So when we say the distance to mu, this thing, that's saying, all right, for every individual, for every group and every individual within every group, that's what the IJ is referring to, we have that individual person's or object's measurement minus the local mean. So what we do is we add up, we do the average for all the people who are in the same group as this person. So this is mean for those in group I. And the dot is saying, well, we just want to make sure we don't care about which person is which. We want to lump them all into one number. Yeah. Good. I'm now making sense of this. And the distance to the big mu, well, that's for every individual. Well, that's the mean of everything. That's why the double dot. Of course, that's not the real, that's not mu, that's the estimate we have for mu. Now, this one's going to be slightly different to your lecturers in a second, but I'll get there. The distance from the local mu to the big mu. Okay. So for every individual in the entire group, I need to find the distance between their local mean and the group and the grand mean and square it and add it on. They all have to be there because every one of them, the distance to the grand mean is the distance to their local mean and the distance from the local mean to the grand mean. So that local mean to the grand mean is counted for every individual. And so technically it's this, right? It's that. So for every j, for every group, and for every j within the group, I have to put this in. But what this means is that this quantity is there, is the same number for every person or individual in this group. And so that's why we end up with, based on how many people are in the group, like that. And that's because counted for every individual in each group, right? And this number here is how many individuals there are in that group. So I find this easier to process than this, like, because there's no particular reason you have to figure them out separately and multiply them and add them because, well, just do them all. Already gone to the effort of calculating everything else. The computer doesn't do that. It just does them all. Yeah. Cool. So, the ANOVA table does the between groups and within group stuff, but that's basically what I'm saying. How far are the local means from the grand mean? How far are the individuals from their local mean? How far is the individuals from the grand mean? And you have those things, but the thing is there's a certain amount of step back just a second. When you do the probability theory calculations, you don't get the correct distribution with the right number of degrees of freedom, and so you do this degrees of freedom thing. It's a distribution finder. K is how many groups there are. Actually, no, it's not. It's one less than the number of groups, I think. No, is it? K is how many groups there are. K minus 1 is the number of variables that go with your grouping with your categories. Yeah. So the reason it's K minus 1 is because you're all comparing them to one of them. And so there's one less variable than categories. Yeah. K is the number of categories that there are. So I'm just going to draw this table. This is me trying to remember and understand what's going on here, so I hope it's useful to watch. So in the ANOVA table, between groups, within groups, total, that's what the thingy says. Okay. And then it has the sum of squares, and that's the things that we just calculated. The sum of distances to things. That sort of thing. And this is apparently called SSG. All right. And this thing is, yep. And it's called error because this is technically our estimate, because each individual, the best estimate we have for them is the mean of their group. And so we're finding out how far those group means are from the grand mean. Whereas this one is how far everybody is from their estimate. Yeah. Okay, so that's the beginning of the table. And the idea is that there's K groups. Or categories, if you like. Okay. So, the only actual measurements involved in this one are the K group means. Really? Because we have the NI, whatever. And so there's K minus 1 degrees of freedom there when I calculate that standard deviation. And even though they all have different numbers of how many times they appear, that's fine. The within groups one, the total has the number of individuals minus 1. And this is all the rest. So the idea is that this plus this equals that. So this plus this equals that. And this plus this equals that. And so this must be whatever's left, which is n minus k. It's actually, I've been told, it's actually inverted commas, the dimensions of the subspaces. Yeah. So there you go. So the subspaces we're projecting onto. There you go. Yeah. Okay. Well, actually, no, it's not. It's the dimension of the perpendicular to the subspaces we're projecting onto. Yes. Okay. So the idea is that you want to take into, you actually technically, what we want to do is we create, when we do a hypothesis test, we want to create a statistic that we know the distribution of. So when you do variances, when you figure out how far apart the squares of things are, it forms a chi-square distribution, but only if you divide by the degrees of freedom. And so this divided by that is a chi-square distribution with k minus 1 degrees of freedom, and this divided by that is a chi-square distribution with n minus k degrees of freedom, and then if you divide two chi-square distributions, you get an F distribution. Named after Fisher, who did it first. And so, sorry? The jump, yeah. And so that's what we're going to do. So this is the, it continues after this. Between groups, within groups, total, sum of squares, df. This is called the mean sum of squares, and this is your F statistic. And then usually there's a p-value here if you look at a computer program. But anyway, so the idea is that this is called SSG, this is SSE, this is SST. The only reason to have the SST is to just make sure that the maths is working out correctly. These two should add up to that. You don't really need this to do it, but it just helps you check it's working properly. So this is SSG over k minus 1. This is SSE over n minus k. So this divided by that equals that. This divided by that equals that. And then this divided by that is that. Oh, sorry, this divided by that is that. So that divided by that is this. Right.
So,
And
I get this from the statistics. So what information?
sorry?
Logically, I don't understand. So I divide.
So we divide this number by this number, and it produces this. And that is a statistic that has been calculated from my data.
Okay.
Right? So I've combined, by this roundabout fancy process, every piece of data in my data has been combined together into this F statistic. Right?
Yeah.
So now, if I want to make a decision about whether I believe something, I can base it entirely on this number instead of looking at my whole set of data. So now I ask myself, if it was true that all of those means were the same, what options could I, for all the places that the data could have been, if I think about all the data that could have happened, and I compare the F statistic that could have happened to the F statistic I have, then I go, gosh, mine's really unlikely compared to those. I don't believe it. And so I conclude that, therefore, the means aren't the same after all.
So what's the minimum I can get?
1, I think.
1.
I mean, the minimum F, theoretically, you can get anything from 0 to infinity. But it would be a weird-ass world if the differences between the group means and the grand mean was 0.
Yeah.
And it would be a weird-ass world if that difference was, it would, yeah, okay. So anyway, it would be a weird-ass world if that difference was smaller than this difference.
Yeah.
Things should be closer to their local mean than to the grand mean on average. And so most of the time, in any real-world situation, especially when you're planning to reject, you're hoping to reject this hypothesis that they're all the same, most of the time, this divided by this will be more than 1. but it doesn't have to be. So the idea is that these are all the F's that could have happened. So if the means are all the same, I should have called them 1, 2, 3, but whatever. If the means are all the same, you know, i.e. the betas are all 0, right? Then this is the F's that could have happened.
Yeah.
And this is my F, and this is the p-value here. And you look at that p-value and you decide at what level of smallness you think it becomes too unlikely to believe this if. Yeah. So it's a hypothesis test. It's just that we get to the test statistic by an extremely roundabout way.
The idea of it is to include everything in this tool.
Yeah, I mean, test statistics are designed, you're supposed to include all your data. And the idea of the way that we've done this is to compare how far everything is from its estimate in one situation to how far everything is from its estimate in another situation. So for us, this is how far the estimates are from, so we've got two stories. One is everything's equal, and this is how far everything is from the estimate when everything's equal. And this is how far everything is from the estimate when everything is replaced by its local mean. And then this is how far those two estimates are from each other. And so what you want is there to be more explanation of variation between the groups than there is to say, okay, if I want to predict what someone's number is, I want the distance between, I mean, really I prefer, this is how far everybody is from their group mean. This is how far everyone is from the grand mean. It would be cool to compare this to this, right? But this is always more than this, so it doesn't really help that much. They compare this to this. There are reasons why, and there's some details that I'm not sure why. But we compare, basically the idea is if all the groups are really close to, group means are really close together, then they probably don't count as different. But you compare it to how much variation there is overall. And in my head, it goes like this. These are the pictures that are in my head of what could happen. So in this one, there's the difference between that sort of SSG, the difference between the group means and the grand mean, and this sort of SSE. The SSE is a lot bigger than the SSG, and so my F statistic will be small. And I'll conclude, since the F is small, it's really quite likely, and so then I'll conclude, actually these groups are quite similar. But if it's more like this, I'm going to put the means in exactly the same spot, right? What if all the data was this? Now the SSG is the same, and the SSE is smaller. F is bigger. So the thing is that even if your group means are really close together, if your variation is really small, you'll still be able to see that the groups are different. So in this one, I couldn't tell when I combine these groups together which group is which based on their location. But when I combine these two groups together, there's actually a little gap between them. So I can see just from the graph that these are different from each other because the variation within the group is small enough to not overlap with the other group. That's the idea in my head. Yeah. Right. And so that's the picture I've got. The details are, there's technical details that make the calculations exactly as they are, but that's the philosophy that's going on. Yeah. Right. Now is that 25 too? Yes. So mild dyslexia, so sometimes I read the clock hands backwards. So, yeah. Not as bad as my twin brother's dyslexia, but, you know, bad enough to slow me down a little. Yes, I do. Though I do remember saying to someone, you know, it's my birthday, 12th of December. I said, oh, when's your brother's birthday? Just think about that for a minute. Oh, because we're twins, right? I do have another brother.
There's always a slight possibility that you were born on different days.
That is a possibility that we were born on different days. I'm the youngest.
Very unlikely that you to be born.
But we're only 5 minutes apart, so the chances are slight.
Because like it can be a few hours.
It can be a few hours, yes. Especially if it's a natural birth. Twins are much less likely to be born through natural birth than through a Caesar. So there you go. And there you go. Okay, so that's my understanding of ANOVA. Now you can do all of that with the X's and stuff. Did we find that or not? Or did we give up on that?
I didn't have to check, but yeah, it happened.
It happened. So presumably it's a regression model, and you can find a prediction for what the betas are, and which would be an X transpose X inverse X transpose B, X transpose Y. And that would be the best estimate for what the betas are, and then you would do something. Don't quite know. And I'm pretty sure these calculations here are figure-outable from the lengths of some vectors involved in that story.
So to set up the matrix, how you set up the matrix, you've got all your ones in the first column, and then your indicator variables are your zeros and ones respectively, and then there it's all set.
I think it's going to be that, like 26.
I think it's a bit later, to the end of module 4.
This is the same logic.
Just so you know, the F distribution needs 2 degrees of freedom to tell you which S distribution you have. Yeah. So, you know, Fville has streets going in both directions, as opposed to T towers, which only has 1 number to tell you which T distribution you have. Yeah. So in my head, all the distributions live in a city.
Is that because is it like there's only one? Is that because the T distribution is symmetric about the Y and the X is not? Or
Yeah, but it's also because the calculation that produces it only has 1 variance in it, whereas an F distribution has 2 variances.
yeah.
And so you need the degrees of freedom for both variances to make it work.
Could you teach us how to learn?
How to learn?
No, how to study? Because I think your way of studying is good. Like you have stories, cities.
Well,
I'm sure there's a
look, one thing I do to make sense of these things is try to put them all in the same place so I can look at them at the same time.
You know, what you might say.
Like a mind map except in your head.
Yeah.
Well, usually it's not, you say mind map but in my head, but often it's a mind map that isn't in my head. So when I studied for exams, when I was a student, I would draw a big thing on my window that had all the things. Or I would get a big piece of paper, the back of the puzzles from 100 Factorial was pretty good, and I would draw everything, and I would write them all down, or I would put them all on bits of paper and put all the bits of paper out. So when I did multivariable calculus in the seminar, I did that, right? I went, well, this is this integral and this is this integral, and I'm going to lay them all out so that I can organise them to compare them to each other. So in this course, you've got all these different situations, you've got different procedures. I would put them all on a separate page and try and organise them by the information that they separate them. And that's another useful strategy, is to say, well, what is it that makes these similar and what is it that makes them different? Because if you know those things, then if you know what makes them different, you can get a handle on when you use one and not the other. But sometimes we try and just keep it all in our head. And actually, philosophically, it's like statistics. One of the things that we do in statistics, in data science as opposed to statistics, is to go, we've got all these measurements and there's lots of variation, and we want to have a way of explaining how that variation happens. And it may be that there's a small number of variables that do a good job of explaining this variation. And so there's only like 3 bits of information we need to predict this. So, when you look at your hypothesis tests or whatever, or regressions that are in this course, you say, well, if I can compare how they're different, it may be that there's only a couple of bits of information that tell you that they're different. And therefore, that's what I need to learn, those differences. Yeah, so that's my advice about trying to make sense of things when there's a lot of information. And in general, it's a useful strategy, and I didn't even know I was doing it until recently. But thinking that way stops it from being so overwhelming.
Yeah. What about the city?
Oh, the city?
Yeah.
I don't know, I just like telling stupid stories. Like,
But,
you know, there's
So
So I have 2 ideas about distributions. One is that there's this angel, right? You know, that well, the thing is that whenever anything happens in the universe, the concept of a distribution is that there is a list somewhere that says everything that could happen and how likely they all are, right? And so I imagine that there's this angel, this great big book, and whenever someone rolls a die, they go, all right, uniform distribution, bang! Opens this great big book, and goes, all right, okay, excellent, that's the number you get today. So I have this keeper of the distributions. But the other thing I have is that actually what that book is it's a street directory. It's like Google Maps. You just go and find where the F distribution lives, and you knock on his door and say, give me a number, and then you take that number, and that's what the number is. And so that's what I think. And so the reason I think that is that the DF in my head stands for distribution finder. And so it's an address to tell you where to find the distribution. And so I imagine this big city, and you're like, Poisson Gardens, where all the Poisson distributions live, and T Towers, which is, a big tower block where all the T distributions live, and Normalville, where all the norm distributions live, and, those sorts of things.
And is standard normal
The standard normal, yeah, I don't know if standard normal's the mayor, but they certainly live in the middle of town.
Yeah.
And there's the parameters of your distribution are the address.
Yeah.
And so the F distribution, it's, streets going that way and streets going that way, and we go to the numerator degrees of freedom, and we go to the denominator degrees of freedom, we knock on the door, and we get our number. And so that's how I think about it. And it's silly enough for me to be able to cope,
yeah,
right? Because sometimes if things are too serious, there's nothing to hold on to. Yeah.
It's really good because you have connections in your brain that you're forming elsewhere. It's not in.
Yeah.
Yeah.
So, and that's the other thing. Deliberately forming connections between things is how you understand and remember things.
Yeah.
The sensation of understanding happens when your brain cells are connected, and the sensation and memory is more likely to happen if things are connected in multiple ways. And so sometimes connecting it to random other thing you thought of is a good strategy, but also connecting the ideas within each other, which is why I sort of started here to go back, well, how, where does this all connect to stuff? And I have a picture that I draw every time where I go, well, what variables are related to what variables, which one's the outcome, which one's the explanatory, so that I can keep track of it. And so this picture helps me remember because it makes it visual, but some people prefer to have a sound, like, some people like a stimulus response thing, so well, you say this, if you say it in the right way, then I'll be able to do it. And if you can transform it into the right phrase, your brain will go, aha, I know what to do. And that happens to us all the time. People say something, and if it's just in the right format, you go, that's like that quote from that movie. And you'll laugh and whatever. And so that's so I have mantras as well, like with this chain rule, just in differentiation, where it's like, well, I would know what to do if that was an X, but it's not. Excellent, that's the chain rule. And when I say it that way, I can tell that it's the chain rule. So, yeah. Okay, let's see if we can get onto this ANCOVA thing with all the other stuff. Yep. So, All right. And it says, well, since it's here, two-way ANOVA is just multiple regression where there's two factors. Now, it only really works if your two factors are only two categories at a time, I believe. So the one-way ANOVA, we were able to turn something that had several categories into several variables that all had two categories. But two-way ANOVA is about having, it only works when there's two, as far as I know. No?
No, we have into
Oh, for the sake of...
Our way was without two categories, but then two factors with
multiple.
arbitrary number of levels.
All right. But then each of those would still have to be turned into multiple variables of their own, right?
So then each one becomes
So alphas.
All right, so it doesn't have to be two. Sweet. Mostly R just does that by itself. It chooses the categories on its own. It chooses the variables that go with those categories on its own, and it deals with it all on its own because someone's taught it how. Presumably, if R suddenly vanished, we would have enough information to reconstruct that if we needed to. Well, you know, think of, you know, the film Yesterday, where he wakes up and the Beatles never existed, right? And he reconstructs their songs from his memory. That's sort of the land that we're... One of the reasons to learn this stuff is that one day we could write a program that does it. So I must tell the stats lecturers that. They'd probably think that was charming, that particular thing to say. You know, what we're doing is teaching you to, one day, if suddenly there were no statistics computer programs for whatever reason, you could write one.
I like to think that some if I went back in time and I had rules, then I would be like boiler. Everyone would praise me for knowing all these things. That would be what? Change to the X.
Let's see.
C to the X. That'd be great.
I'm just... Come on.
Such a fucking cunt. What do you want to say?
Wow, that's really complicated, isn't it? Like, if you just look at this. Yeah, of course. It's just obvious.
Yeah, isn't it clear?
Yeah. If they were both single categories like this, then you could go y is like that. And it looks very similar to what we had before, but before the x1s and the x2s weren't independent of each other. They were just our way of conceptualizing one variable, but we turned it into two. But these are properly two different variables. So something like trying to predict whether a person's, you know, how many hours a person's going to spend in volunteer work, you could use, you know, are they male or not male, and you know, were they born in Australia or not, for example. And, you know, you might really prefer there to be three categories for gender, but we'll deal with that elsewhere. So, yeah. So it's really that you've got two different things affecting an outcome, and they're both categories. The thing is, it may be that this thing and this thing, that this thing has a different effect on that for different values of this. So at the moment, the drawing looks like, well, if you want to figure out what the y is, then you figure out what you go, x1 will give you a little bit of extra, and if you say yes for x2, then there'll be a little bit of extra as well. And it doesn't really matter what x1's doing; you'll always get the same extra for x2. But it may be that the amount of extra you get when you're in yes for x1 is different to the amount of extra you get when you're in yes for x2. Sorry. is different depending on whether you're yes or no for x2. So it may be that x1 affects the way that x2 affects y. That's called an interaction effect. And so it may be that you have these two things together. Their combination produces an extra effect on y that isn't covered by considering them separately. And this is called an interaction. You can also imagine it, I'm just going to draw this. You can imagine it like this, that x2 affects the way that x1 affects y, but they're sort of symmetrical usually. And so you usually end up with something like normally multiply them. Because if you multiply them, it'll only be 1 if you're in both yes categories at the same time. So the idea is that there'll be a bit extra you get for being yes for x1, a bit extra you get for being yes for x2, and then a little bit extra you get for being both yes for 1 and 2. Yeah, so that's the traditional way of setting up an interaction if you've got 0, 1 variables. But you can have multiple categories if you don't draw it this way, but instead you draw it with the like this way, with everything near its group mean and the group means and the grand mean and all of that. You can set that up with as many categories as you want. You just end up with combinations of categories. And so I think the way it works is if you have 3 here and 2 here, then it's really 6 variables, technically 5. Like, yeah, there's technically 4 categories here. Yes for this and no for this. Yes, no, yes, yes, no, yes, no, no. And so I think that's what's going on in the background. And each of those blocks have a local mean. Yeah. And so when you do your two-way ANOVA table, I don't know how you do it with the big design matrix X, but I can imagine how I do it with the ANOVA table like this. Well, crap, it's not on the screen. The ANOVA table like this, where I can look at all the row effects of the x1 variable and the column effects of the x2 variable, and where you look at how far every row group mean is from its column mean. Yeah. Yep. And the residual is how far each of the distance to both the row and column mean and the other mean. So there's a lot going on there. So here's the question. Those two F statistics, right? So this F statistic is saying how much variation there is between the groups defined by category 1 and the grand mean. And this is how much variation there is between the groups defined by categorical variable number 2 and the grand mean. And you can compare them to the total amount of extra stuff. And so this one should be able to tell you whether there is an effect of whether the beta that goes with x1, well, or all the betas that go with x1 are 0 or not, and this one's all the betas that go with x2 are 0 or not. Okay. Now we have interaction. So this IJK is now which position within variable number 1 you are, which position within variable number 2 you are, and then which individual you are within that block. Okay. So I'm presuming that your lecturer would write one of these for you if they're a nice person, so that and you would just have to interpret it correctly. And so this is the effect of being of yes for category for x1, and this is the effect of yes for category 2, and this is the effect of being in both of them at the same time. No, this is the effect of being in position option 1 for category 1 for variable 1, and option 2, yeah, gotcha. And this is the interaction. So they're all defined by MS error. What is this capital I? Do you think that's the number of categories in that categorical variable? Yeah. Gotcha. Capital. So I goes from 1 to I, that's the number of categories. That's the number of categories within that categorical variable. J goes from 1 to capital J, that's the number of categories within the second categorical variable. Well, I'm presuming that capital K is how many individuals there are. So this one is under the assumption that every group has the same number of individuals. Gotcha. So that this is that every combination of categories has the same number of individuals in it, because it's not like you have a Ki and a Kj. Just a second, I want to. So this is basically saying there's, I categories here. J categories here. And then if we go which value of x1 there is, these are all the categories for that. And these are all the categories for that. And then there's like K people, or whatever they are, cats or doctors or houses or mosquitoes, in every one of these boxes. Okay. That's the picture that I'm getting from the way this data is, this thing here is written. So this K is how many individuals there are in the entire, in each category, like in each combination of categories. And so the total, therefore, not entirely sure why it's I times J minus 1 instead of I times J minus 1, I times J times K minus 1. Yeah.
I think he's got two constraints we put on.
Okay.
To fill that up parameters.
Right, yeah. Not that we use that one anyway, so it's okay. It's all good. So the things aren't going to add up the same anymore as they used to. So when it actually comes out, these are the x's. So this is a two-way ANOVA here, and this is what R produces. This is the ANOVA table that R produces when you do that two-way ANOVA. And I think I may have forgotten to turn my microphone on this entire time. Well, there you go. There is one in the bench. But it will have gotten quite quiet when I was over here and much louder when I was over here. So this F statistic was made by doing this divided by that, I imagine, which makes sense. 900-ish divided by 9-ish should be about 100. And this statistic is made by going that divided by that. And this statistic is made by going that divided by that. And so this p-value this p-value here is saying, well, if the null hypothesis that all of the extra bits that go with the interactions, all of the differences between those means and the local means are 0, then my F is rather likely, so I think they actually are 0. Whereas this one is saying the DRV, whatever that variable is, does seem to have an effect on the result. The trans seems to have an effect on the result, but they don't have an interaction effect, so you don't have to, DRV doesn't make a difference to the way that trans makes a difference to the result, or vice versa. So they don't interact with each other. You don't have to consider the actual combination of categories to be able to figure out what to do, what to predict the result. Okay. And so then we did it again by removing the interaction because it wasn't important. And they're still both significant statistically. And that's what we get. Oh, this is a whole different way of doing it.
That's like a different ANOVA, like you like reduced model speed.
Yeah, that's comparing one model to the other model, right? So technically, this 0.8276 should be the same as this one.
Yeah, because they're the same.
Because they're asking the same question. And actually they're doing the same calculation. And I find it easier to think about these questions in terms of this picture, because then I can tell if they're asking the same question. They're asking the same question, they should, and it's a yes or no question about this feature of the drawing, so therefore they should give the same result. Yeah. Just like a t-test, an unpaired t-test should give the same result as an ANOVA on using the same data. P-value wise anyway. Okay. So in ANCOVA, predictors can consist of both categorical and continuous variables. What the frell? Oh, I see. Ah, très intéressant. So it's essentially a regression with an interaction between a categorical variable and a continuous variable. Yeah, I'm going to have to stop shortly. So in my head, it's something like this. No, that's not X. This one doesn't have a name in this thing here. I'm just going to call it C for category. So this X is a number, this Y is a number, and there's a category as well. This is what ANCOVA is doing, and it may be that there's an interaction between these in some way. So the C, in fact, it's actually easier to think about it like this, that the C may change the way that X interacts with Y. So the C actually affects the arrow from X to Y. I find it easier to think about ANCOVA like this. Because what you could have, that Y all right. So this is a traditional regression that doesn't involve the C at all. Like that. It could be, I'm just going to do it with two categories here because it's easier for me to think about it that way. It could be that you have it's going to be in a bad order, I'm sorry. This is just how I'm thinking about it. Okay, so it could be that that the C affects the Y separately from the X, and so you get a little bit of extra from the C being 1 or 0. All right, so you have essentially the beta naught changes when C does, right? That's the idea. Or it could be that the beta 1 changes when C does, but you could have this other thing, right? Something like that. It could be that the beta 1 itself, which is what this is affected by the C. Yeah. I'm making this up, it probably doesn't match what your lecturer is doing, but I like to think about it in this way. And so you've got a little bit of, oh yeah, that makes sense, that makes perfect sense, because it's the same as this. So that's an interaction term there. Sweet, good, I feel good. And so these are called parallel lines. They all have the same slope regardless of what C is. These ones, so what's your lecturer do? So separate lines, you get well this is what your lecturer calls identical lines, and this is what your lecturer calls parallel lines, and this is what your lecturer calls separate lines. So we have B0 and B1 change when C does. And your lecturer calls this identical lines, and it calls this parallel lines, and calls this separate lines. Cool. I'm feeling good. So if you just put them if you just put your categorical variable and your numerical variable into R with this formula, right, where you go C plus X plus C times X, it'll do it for you. And to see whether the slope changes, you'll be looking for what beta 2 is. To see whether the intercept changes, you'll be looking for what beta C is, and to see whether it changes with X at all, you'll be looking for what beta 1 is. Yeah. Okay. My recording's about to stop, so I'm just going to stop. When's your exam?
Saturday.
Good-o. I will not return to the Maths Learning Centre until Thursday afternoon because I'll be doing revision seminars up until then. So if you want to talk to me in particular, then that's when I'll return, just so you know.
What about the SAM version seminar?
Yes?
It's kind of similar. I don't have to recover too much.
Do you want to go over the same?
Yeah, like, depends on what you're doing.
I don't know. No one's asked anything yet.
What if we ask?
No,
No, it's really similar. We did the same thing. So, okay.
Probably. I don't know. I wouldn't give this one to Sam because I've referenced this lecture notes, but
Yeah.
no one's asked me anything for Sam yet, but I have a feeling I will probably talk about this, based because I'm not recording anymore, am I?
Because I remember last